My name is Ferhat Terata from Yale University. In this video, I am going to present a tool that we developed to automatically detect single-trace power side channel vulnerabilities in constant-time cryptographic code. This is a collaborative work between Yale and TII Cryptography Research Center. Rugisa Piskac and Jakub Schäfer are from Yale, and Victor Meteo is from TII. First, let me motivate you with our tool by introducing a vulnerability that our tool is able to detect. Crystal Kyber is NIST's recommended algorithm for the post-quantum cryptography. There is a single trace power side channel vulnerability that is shown in Kyber's message encoding at line 8. The mask value is carried to coefficients, each of which can be either all 0 or all 1, represented in hexadecimal notation as 000 or FFFF. In fact, the complete shared secret has been demonstrated to be extracted from a single trace by different authors. Here you can see the partial disassemblies of the same code, compiled with no optimization and with optimization. The red star symbol indicates that the instruction is a point of interest for an attacker. On the left, in line 8, 9, 10, we have destination register R3, which is vulnerable. On the right, in line 4, destination register R2, which is also vulnerable, because all takes either all ones or all zeros. The shared secret, when optimization is turned off, the shared secret can be read from an oscilloscope display directly with the naked eye. In the optimized code, the attacker needs to profile the exact location of execution. So, all in all, our tool is able to detect and quantify such vulnerabilities and more over disassemblies. But first, in order to develop a formal framework to reason about vulnerabilities, we need to define the leakage model, right? But can we relate different data values that a register takes with power drops and increases at the exact location? The answer is yes. In the literature, almost all power and EM attacks rely on the observation that the data-oriented power consumption correlates with the Hamming weight or the Hamming distance of the registers or the bus of actually any target devices. Hamming weight is the total number of ones in a register, and Hamming difference is the number of toggle bits or the edit distance between the two consecutive states of the register, such as here R1 transitioning into R1 prime, maybe after microcontroller execute an instruction. The graph shows the average of 1000 power traces collected from an ARM Cortex M4 microcontroller with random input X executing f of X. F of X consists of five instructions only. The code is the same and only data is different for each execution. For instance, the green line here shows f of X's signal behavior when X, Hamming weight of X, is 6. Actually, they are all Hamming weight classes are clearly distinguishable, such as Hamming weight 6 compared to Hamming weight 1, right? So if the difference is large, it is more distinguishable. We also introduced the notion of differential Hamming weight in order to totally order each signal behavior to support differential Hamming weight register analysis technique, which I will introduce momentarily. Our tool, Pascal, takes an input of a binary executable, and security inputs should be marked. Then it automatically identifies leakage locations, as known as point of interests, and generate test vectors that actually exercise different types of power consumption behavior. It uses Angular framework to disassemble input binaries and to obtain symbolic expression of registers in bit vector logic. In Pascal, we introduced two register analysis techniques: symbolic register analysis and differential register analysis. The former relies on sampling queries using a bit vector theory solver, such as in Z3 and CVC5, whereas the latter one relies on optimization queries using an optimization solver over bit vector logic, such as Optimat SAT. Let's take a look at the differential register analysis technique. I will use this simple code throughout the presentation, which performs a conditional execution written in a constant time style, meaning that there will be no timing side channel basically, because there is no explicit branching here, but it performs a conditional addition, right? S represents the state of the register file, which can be thought of as our symbolic store, consisting of only registers from here R0 to R4. At this stage, we perform binary analysis and identify tainted registers and harvest symbolic expressions through the symbolic store, but in a lazy manner, only for tainted registers. In the example here, the bit width of inputs are X, are 8. Secret input is X, and secret tainted intermediate values are marked with red color. Beta and lambda here represents the unconstrained input, which represents any numbers in the given bit width. For each state having tainted registers, such as S2, we generate a verification condition using relational symbolic execution over fixed bit vectors. Here we need to relate two executions such that they should have this joint two secrets, and we compose symbolic register R1 here and rename it as R1 prime and compose it with itself. However, verification conditions are not enough for us to quantify large Hamming weight swings, right? Therefore, our method employs single objective optimization queries to obtain the maximum and minimum Hamming weight differences. As we've seen before, large Hamming weight swings are more distinguishable for an attacker. Here you can see that S2, at state S2, the difference between the maximum and the minimum Hamming weight is 0. This can only happen when all zeros and all ones are present. This kind of large Hamming weight swings are usually the attack points for adversaries, right? And here, adversaries. Let's now quickly look into the symbolic register analysis. It's an approximate model to obtain the entropy of destination registers and quantify the leakage over the single trace. Each Hamming weight class has its own probability, and they are not uniformly distributed. For instance, Hamming weight 4 over 8 bit width numbers and contains 7 different values, 70 different values, whereas Hamming weight class 1 contains only 8 numbers. Sorry, here Hamming weight class 1 contains only 8 numbers. Here on the same table that we discussed the Hamming weight leakage model, S2 and S3 have an entropy of 1, whereas other states should have 2.54 according to the probability distribution of with 8 numbers. Now, at this point, let's get back to the Kyber's message encoding case. Line 9 can take all ones having Hamming weight 16 or all zeros having Hamming weight 0. Therefore, the difference is 16 and the entropy is 0. Entropy is 1. This is another vulnerability from the literature on the lithium. The lithium is the recommended signature algorithm of NIST for post-quantum cryptography. The polynomial generation here looks how many negative and positive coefficients the private polynomial has. In this case, the Hamming weight swings between 32 and 1, and the difference is 31. This is an interesting vulnerability which shows there are some attack points that can happen at registers taking only a few values that are not limited to only two, like the cases of kyber and dilithium that we have seen before. The ArcSparks of the Sparks lightweight cryptography algorithm is an example. Line 7 calls a rotate left for 16-bit registers. Jan and Oswald demonstrated an attack at this point. Let's look at the report that Pascal generates for the ArcSparks over an optimized binary. This is actually the optimized assembly of the whole ArcSparks code, basically. The maximum Hamming weight is 2 and the minimum Hamming weight 0 at line 10. Over the set of 2 to the 16 numbers, the register are 3. At line 10 can take only one of 0, 1, 2, 3 or 3. Then therefore this reduces the number of traces required for the attack significantly. However, their Hamming weights are very low and close to each other. Therefore, the single trace attack seems not possible. And the authors needed to create templates and profile the device carefully. So, in summary, we developed a tool to detect and quantify single trace power side channel vulnerabilities by introducing two different register analysis techniques. We identified 30 distinct vulnerabilities, and many of them have been confirmed by different attack papers in the literature. More information regarding the algorithm, the literature review, and attack against project and implementation as well can be found in the original paper at this archive link. These are the references that I used throughout this presentation. Thank you.